Hello, it's a pleasure to be speaking at this workshop. I'm Alan Yuille from Johns Hopkins University, and I'll be talking on compositional models and occlusion. So, the workshop, as you know, is on recognition from low quality images and video, and how good are current state-of-the-art algorithms for recognition and detection in these sort of non-ideal visual environments. The workshop includes a whole lot of work on, low quality, motion blur, etc. But my talk will focus only on the issue of occlusion. So occlusion, for reasons I'll discuss, I think is really important, particularly because it's ubiquitous. It's really common in the real world. You hardly ever see an object that isn't occluded, but it doesn't happen so much in in data sets. So robustness of human recognition under object occlusion. So humans are really much better than deep nets for object classification if there is occlusion. So there were experiments done, Hongru Zhu in cognitive science last year, and also some work, Adam Kortolevsky, we did some studies, WCCV, take an object like this, a car, it's occluded by a dog and some other animal. You can vary the amount of occlusion by varying the amount of objects in front of the car, and you can see how well humans perform on this, and you can compare it to deep nets. So humans do pretty well. Blue means sort of almost perfect. What the humans occasionally do is that they mistake a bicycle for a motorbike. That's where the things happen, and that's possible, particularly if there's a bit of occlusion. But the deep networks don't do very well. Here's AlexNet. That's sort of they tend to get it right more often than not, but they're by no means like humans. ResNet, also not very good. VGG, a method called two-stage voting that we were looking at, which is like a simple type of compositional model. I'll discuss compositional models a little bit later. So this is more like a compositional model that generally did actually quite a lot better, but still is not actually, is still some way below human performance. So it's something that humans can do pretty well, and current algorithms, computer vision algorithms, can't. So how to deal with occlusion? So I've said it doesn't show up a lot in standard databases, so you could do the standard deep network approach, means you just make your training data set bigger. You get images which have more and more occlusion, and you train on those. But there's a problem. There are a combinatorial number of ways that you can include an object, which is the product of the number of positions of sizes of occluders times the number of occluding objects. So there's a combinatorial number of those, and you can ask yourself, will training on a finite sized data set be possible to learn to deal with this combinatorial set of possibilities? Well, I don't know the answer to that. Perhaps if deep nets are smart, they might be able to do it. You'd show them a finite set of a combinatorially big set, and they could still work. But maybe deep nets are not smart. Maybe they're only able to memorize and interpolate, in which case they may not be able to do it, because a finite set is just tiny compared to a combinatorial space. The examples you have trained on will not be representative of the full space. And there's a bigger picture here. So I'd argue that in fact there is a problem on how we currently evaluate the performance of vision algorithms, because what we do is we set up a finite size balanced annotated data set. So the acronym for balanced annotated data set is BAD, B-A-D, but the space of images is combinatorially big. You can generate images in a combinatorial number of ways, and so finite size balanced annotated data sets may not be sufficient to train and test recognition algorithms, because they're a finite set and that's very small compared to a combinatorial set. So, and in particular for occlusion, objects can be occluded in a combinatorial number of ways, but occlusion is just one more example. If we're working in a space which is combinatorially big, testing and training on finite sized data sets, as we've been doing, is problematic. And there's an opinion paper on arXiv with Chengxi Liu which describes this. Okay, so now it's also perhaps good to consider human versus deep nets and what humans can do. So I know, there were papers saying how deep nets are far better than humans, and I'm usually, a few cases that's right, but most of them, if you look into those papers in detail, you find it's rather misleading. So I think human vision remains the gold standard and for computer vision, but it also outperforms computer vision in several dimensions. Task generality, a deep network is usually trained to do one task or maybe two or maybe three, but human vision does multiple tasks: detect objects, parse them into parts, estimate 3D configurations, find boundaries, and many more, all at the same time. Learning efficiency, an adult human can learn an object just from a few examples by exploiting prior knowledge you have about objects. Like, you see a new car, you know a lot about it because you've seen so many cars in the past. Robustness to viewpoint changes, novel context, partial occlusion, etc., and the pixel level image attacks. I realize robustness is really, of these points, robustness is perhaps closest to the spirit of this particular workshop, but I did want to bring in this more general picture. Domain generality, humans can learn on one image domain, real images, line drawings, visual art, and perform well, among others, while deep networks typically perform well only in training set domains. I was on an exam where a student had done very nice work on counting the number of people in crowds. He had state-of-the-art results on 3 different data sets. The only problem was that his algorithm, if he tried running it on he trained on the first data set, applied to the second data set, it gave really bad results. So his algorithms were able to fit the data sets, but they couldn't transfer between them. So there were all these types of properties that humans can do, machines are not good at, and today robustness, particularly to occlusion, is what I'll be dealing with. So classic ways to deal with occlusion. Well, once you get to my age, you realize that the history of computer vision is cyclical. Ideas get invented, forgotten, then rediscovered, then forgotten again, rediscovered. So to some extent we've been going round in circles since the late 1970s when computer vision got activated. Fortunately, it's a bit more positive than that, because instead of just going round in the circle, probably we're going more in a helix with a vertical dimension, and each time we invent an idea, we do better at it because we've got stronger techniques and better computers and things of that sort. So I want to mention the classic idea, robust templates for dealing with occlusion. You represent the object. This has to be single viewpoint only, so there are caveats about how well this works, by a template which captures the spatial structure of the object's appearance. Then you compare the difference between the template and the image. You use a measure of similarity, which is sort of robust to outliers, which would be occluders, and then you detect the occluders by thresholding. So there's even a neural network version. The first time I ever saw this was in a paper by Tervo Kohonen in the early 1980s, and it's in a book, Self-Organization, Associative Memory. He had ability to detect faces in presence of occlusion. For another method, classic method from work of one of my students, and this is now going back 25 years ago, you represent an object like a motorcycle helmet in terms of principal components. These principal components are to deal with different lighting, because the helmet could be like any other object. The helmet could be lit from many different directions, and you want a model of the helmet that can deal with the different lighting, and this principal component method was a way that you could do with it. But then the residual, the part of the image that could not be explained by the principal components, corresponded to the occluding object and also to specularities. Why specularities? Well, because principal components model for dealing with variable lighting assumed Lambertian models, didn't apply to specularity, so the specularity was not explained by principal components. So here is an old paper, 25 years old, Russell Epstein, now a professor at UPenn. Here is the image. Okay, you see a motorcycle helmet, a specularity here, and a vertical bar. Here is the reconstruction. Not a great image because this is 25 years ago. Here is the residual, the part of the image that hasn't been explained by this PCA model. And if you threshold it, you see first, okay, you detect the occluder, you detect this. So here shows that you can detect occluders under limited, under certain restricted views, because they are parts of the image that cannot be explained by the model. The critical thing is you need to have a template or PCA model which specifies the appearance of different parts of the image, or the spatial pattern of the image in terms of the, underlying model. And then the occluders would explain everything that isn't explained by the model. Okay, so now that's history, last century. So how to compete now with deep nets? So these classic models only worked for single views on an object and only for a few object categories. Okay, now, but deep networks are far more complex. Okay, so how can we extend those ideas to deep nets? So the key insight is that you formulate deep nets by making them more generative. And this was done in this work I'll discuss by replacing the head of the deep network that usually does classification by a generative model on the deep network features. Now the generative model must be smart enough to predict the image or the image features at different positions, conditioned on what object it is and on the viewpoint. So if we have a compositional net, a generative network that has this has these properties, then we can make it robust by introducing an occlusion process saying that some particular region of the image, which the network has to find out, can be generated by some other process. This will make it robust to the occluder, but will also detect and localize the occluder. Now to do this, because this is computer vision, we have to show that these models perform as well as standard deep networks if there were no occluders, but outperforming them when there are occluders, and moreover that these models do not have any extra information in them that was not supplied to a deep network. Okay, so here occlusion is common even in some BAD datasets. So this is COCO. COCO has lots of objects. In many of them, the amount of occluders is not very big, but you will, if you check through COCO, you will find some examples where there are occluders, fairly heavily occluded, and so you can isolate this set out from COCO. You can put them into three different groups. One is extreme occlusion, heavy occlusion. One is medium occlusion. One is low occlusion. Okay, so occlusions are Heide variable in terms of shape and texture. Even these images show it. Okay, a frisbee, I think a dog, a tree, some vegetation, I think part of a motorbike with something strapped on front of it, which is occluding the motorcycle behind, somebody doing skateboarding with a skateboard, and some fence here, and an airplane with a whole bunch of, because I'm not quite sure what this is, maybe the airplane's on fire, etc., or human. So objects can be occluded in many ways by many different types of objects, so arguably exponential complexity, which means you can't really store all of those or represent them nicely in a finite size data set. So the vision system must generalize to exponentially complex domains. Okay, so deep nets perform poorly on occluded data and don't generalize well when trained with non-occluded data. This isn't, I'd have to say, as someone of my generation, this is not, this is a bit of a strong statement, because compared to previous models that we had, deep networks do very well when there's occluded data. Before deep networks, we had probabilist parts models. They worked reasonably well. They could deal with certain types of data, and certain types of occluded data, and they worked well on Pascal. But generally, object detection did not work at all when there was much occlusion, and so deep networks are a jump ahead of that. However, as you increase the amount of occlusion, performance starts going down. No occlusion, almost perfect, 30%, 88, 50%, 78, 70%, 63 with a VGG network. This is all evaluated on, I think, COCO. Then the next thing you do, if you're a neural network, is say, hey, we just need more data. So you train with augmented data, you throw in a whole bunch of random occluders, and you improve. You certainly improve. 70%, you're now up to 80%, but you're still not doing well, but compared to human performance, which would probably be almost 100% here. Now, is this a big jump? Well, this is a big jump, and but again, to give a slight perspective, it's a big jump now with deep nets. It's still a fairly big jump when deep nets started, but even then, big jumps were expected. When deep networks came in to vision, 2012, 2013, 2014, you could get algorithm improvement that was going like 10 AP or more. This was fairly standard. If you were clever enough to be the first person to apply a deep network, or the right type of deep net to a particular problem, you could get these huge advances. Now, you get very, very clever people, very, very many of them, working with very, very large numbers of computers, and they're struggling to improve performance by 1 AP or 2 AP or something like that. So, anyway, so here, augmented data, occluders can improve things quite a lot if you're used to thinking of improvements in terms of 1 AP, but not really significantly. And we've got arguments for that about the combinatorial number of data that you really need to train. Okay, so let's get into comp nets. So here is a standard deep network. You have convolutional layers, and if it's VGG, you have a fully connected classification head that makes the decisions from these low-level features. Okay. So now what we do is we cut off the head, we keep the bottom part, we keep the compositional layers. So at the top we've got a dictionary, we've got a set of feature vectors in particular rectangular region, height and width, etc. Okay, and now we introduce on top a generative model that predicts the feature vectors here. So here are a few mathematical equations, the feature vectors at different positions. So FP is the feature vectors a particular position, capital F is the feature vectors all over the position. We're assuming a fairly simple factorized model. Probability of the feature vectors over all spatial positions is the product of the probability of the feature vectors at each position. That's conditioned on certain parameters, simple mixture, simple distributions I'll show in a minute, and so which is specified here. So what you should think of is you think of an object like a car. The car wheels will be somewhere around here, and because all car wheels look pretty much like other car wheels, there will be a probability of feature vectors in this place that look like car wheels. Okay, and that will be captured by this equation. Okay, and here's a little bit more technical stuff, and all these feature vectors are normalized, put on the unit sphere, etc. Okay. So now the network assumes that for each object there are a set of mixtures, it has a set of mixtures which correspond roughly to the object seen from different viewpoints, and then from each viewpoint there will be a generative model for the image features. The top level features will be these in this VMF kernels, which we'll illustrate later, which are intended to sort of abstract out or take out from the feature vectors the most important ones. So the head is now all this component here, object, mixtures, generating onto the feature vectors here. Now I want to emphasize that this is not hand trained. The mixtures, all this part is learnt in an unsupervised manner by the compositional network. It just has the same information as a normal deep network. Okay. So VMF likelihoods, probability of the feature vectors at a particular position, given the state here, mixture likelihoods for different viewpoints, etc., and class scores for the object. Okay. So the inference for this model, after it's been learnt, can be done feed forward, well, almost entirely feed forward like a deep network. It's just everything up to here is standard. Once you get from here up to here, you're computing log probabilities and things like that. And so it's nonlinear operations that you don't have in a normal deep network, but still it can be computed in a hierarchical sequence from here up to here to get the total scores for a vote for each object from each viewpoint, and then you just take the maximum score to find which object and which viewpoint are considered. Okay. To learn them, you learn them by combination of backpropagation and clustering. The clustering is needed to find the mixtures, and that's again unsupervised. But still, you've got an overall loss function here, and you're minimizing it by steepest descent backpropagation, but also by the clustering. Okay. Now this is reasonably explainable. Remember, the model is intended for each mixture to predict the feature vectors, so we'd like the feature vectors to correspond, if possible, to different parts of the object. Okay, and so with all the feature vectors here, they're sort of summarized by these VME kernels at the top. And so to see what these VME kernels are doing, you look at which image patches activate them most. Okay, so the kernels, crudely speaking, intuitively would correspond to parts of the different objects. Now in what I'm showing here, we have been concentrating on vehicles. So you'll find that some of the VME kernels, one of the VME kernels will like airplanes, but in particular airplane engines connected to wings, as shown here. Another part will like parts of the body of an airplane, the part here with a bunch of windows in them. Okay, and perhaps as a point of generative models, there's increased interest in doing generative models on images, and we're doing them instead on feature vectors. So if people who know about generative models might wonder why. Well, we're doing them on feature vectors because we want our generative models to be invariant to details about the particular objects we're looking at. So at the intensity level, these examples, these parts of the plane will look different. They're going to have windows in different positions, they're going to have different patches here, they're going to have different airlines written on them. So we want something that is invariant to those types of details, and what better than deep network features, because they are trained entirely not to care about the particular details of a particular airplane, but to care about the general overall appearance. So a generative model works on at this sort of level, and so the function of the deep network features are to get a representation that of the image which is invariant to little details about whether this is Nada or Berlin or Nada or whatever these, or JetBlue, whatever it is. Okay, so getting back to the kernels, other kernels will correspond to the seats of motorbikes, and again, because they're deep network, it's built by deep network features, they're invariant to some of the, to the color and other properties. Another one will correspond to pieces of the bicycle. Okay, so explainable in terms of the parts, roughly. Class mixtures, they correspond roughly to different viewpoints. As I say, that's not enforced, because when we're training the models, we don't know what the viewpoints are. The algorithm just knows that there can be certain views that look very similar to each other and other views that look very different. So if you do this on bicycles, you find one mixture corresponds to bicycles seen from the side, another one corresponds to tandem bicycles where you've got two people, three seats, two seats here as well as a handlebar, two people riding them, which does look different from these. Other mixture components correspond to viewed from one side, viewed from another side. Generally in these models we've stuck to 4 mixture components for simplicity, but there's no reason why you shouldn't go up to more than that. Okay, but so the mixtures have some interpretability, and so do the kernels, which is necessary for the idea that this is a generative model, meaning that we can that it not only knows the object, but for each object, for each viewpoint, it knows roughly what features should be in what particular parts of the image, because that was the property of the templates and the older models, last century models that I described at the beginning of the talk. Here is something about explainability just in more detail, but I'll pass that over and move on to the key aspect. So the key aspect is to make it robust to occlusion. And so, as what I said earlier, you have the generative model for the features, objects, mixtures, etc. But now you can put in an outlier process that generates occluded kernels in different parts of the image, or has a probability of generating them in different parts of the image. So your generative model has a probability for feature vectors at each position in the image. The occluder model can compete and say, hey, maybe it's explained not by your generative model, but by some of my occluder features. Okay. So outlier model, I'd have to say this model is not actually trained at all, because part of the point of this of being robust to occluders is we don't want to care about how many occluders there are, whether it's extreme or not. If we did, we could train the occluder model to make it better, probably improve performance, but we deliberately don't want to do that, because that again would be falling into the trap of trying to overfit the data set. Okay, so here it is, probability z is a variable at each position. Z equals 1 says it's going to be generated by the object model, z equals 0 means no, it's switched off, it's generated by the occluder. So we've got introduced this new variable z, and so we need to estimate it when we're running the algorithm. If we estimate z equals 1, it says a particular fixer point is explained by the model. If z equals 0, we're saying no, it's explained by the occluder. Okay, and so the occluder model has kernels. What are they? Well, they could just be anything that the model doesn't look like. So you could just get them by taking a data set here and just training on those, training this part of the network, and getting a dictionary of possible patches that just don't look like the object. Okay. So then when you run the algorithm on the image, there's sort of competition between the object and the occluder model. So from this image from Coco, here is the car, and most of the car is explained by the object model, but the tree, this vertical bar, this head are explained by the occluders, and so that's switched on. The z variable is equal to 1, so it means we can isolate the occluders. Same here, etc. So we don't know anything about the occluders except that their appearance is typically different from the appearance of the car that we're looking at. You can then quantitatively evaluate this. You can use occluders which are just wide, occluders that are noise, occluders that are random patterns, etc., and occluders which are humans, objects painted on, and you can have reasonably good ability to actually detect them and localize them. So we can then classify these objects fairly well. We can jump from the performance of the VGG type things up to this level of performance, almost 90%. We can do this, we can also train our deep network a little bit with the occluders, as we did for the deep nets. That helps a bit, but really it's the structure, the generative model, and the occlusion process that makes our method better. Okay, so that was CVPR papers. They were sort of done on 12 objects, I think. We've now done it on 50 or 100 appear in the journal paper. So it's still generalizing. It's particularly good, I'd have to say, on vehicles, because certain of the assumptions are more likely for vehicles, i.e. that there are a set of mixtures, and if you have the particular mixture, the spatial pattern is very reliable. That's less true for some of the more complex objects here, but nevertheless the same, similar results are happening. Okay, so ImageNet's under occlusion, not performing as well as we did for the vehicles, but we're performing quite a lot better than we do if you just do ResNet or something of that form. And I say for the compositional networks, I think this is a starting point, not an endpoint. Now what about object detection? So the deep nets also have a problem for object detection as well as for object classification, because they first have to find where the object is and then classify it, and that part, the detection of where the object is, can be also ruined by occlusion, particularly occlusion that you haven't trained on. So we modified the comp nets to do this. This is not, this was rather different. It wasn't the same as just using the standard comp nets, because there was a problem that came up, which is that the context has too much influence when an object is occluded. By context, remember that when you train a deep net, you're giving the image a rectangular box. That rectangular box contains the object that you're learning to detect, but it also contains the background. And so the deep network doesn't know which is the object and which is the background, because all it's given is a rectangular box region. Okay, so it, being smart, it uses the context within the box to try to identify the object, so it relies on context. Now that's smart, but what's not smart is that it doesn't have a mechanism for switching off the context if the context is incorrect, because it doesn't know within the box which part is the object, which part is the background. So what we can do is separate the representation of the context and the object, because you know what the context is for airplanes. It's usually sky, and by exploiting that you can even effectively segment the image while you're training, without again actually knowing where the boundary is. Okay, so here, project here, this area here could be explained more by the context model than by the compositional net. Hence the compositional net can find the airplane here. It makes a few mistakes with these bits, but basically it gets the airplane, gets the car, gets the bike, and knows that this is the background. So it's able to have the concept of having a foreground region and a background region, and the background region is context. The context could be helpful, but if it's not helpful, the network should be smart enough to switch it off. You do that again by having an outlier model that essentially says, forget it, this isn't the context we want. So if you're trying to detect this airplane that is fully occluded, what you really want, you don't want this box which is too small. You want the blue one here, and if you don't deal with the context, what you get is this big blue box, because, well, there's a lot of context, there's a lot of blue sky in there which gives evidence that there's an airplane, but it's blue sky is in the wrong location and there's too much of it and there isn't much of an airplane. But the poor deep network doesn't know this, because all it's taught is airplane. It's given a bunch of these rectangles, doesn't have the concept of foreground or background. So deep network, compositional network, can deal with this and can also detect objects in presence of occlusion fairly robustly, and again detect the occluders. So again, you're up by a reasonable big jump over the standard occluder, standard deep networks, which again are not very good with occlusion for detection. I mean, better than anything was before deep nets, but they're still not as good as humans, nowhere near as good. And comp nets still not as good as humans, but we're closing the gap. We're still performing pretty well, but does require models of the context as well. Okay, so I've reached about the end of the talk, so roughly on time. So here is a conclusion. So so I'm interested very much in occlusion because it's something that's very important in reality, does give rise to low quality images, etc., and we need to deal with it if we want vision algorithms to work in the real world. I also have a bigger agenda that I picked occlusion because it's an example of exponential complexity in the data, which can cause problems for algorithms trained in the current fashion on finite data sets. So vision in general, images are combinatorially complex, and finite size balanced annotated data sets are not a good way to evaluate the performance of algorithms if there is combinatorial complexity, because no finite size data set can be representative of combinatorial complexity. Deep nets might be able to do it from finite size if they're very smart. I'm not sure they're smart enough. Our experiments suggest that that we know they're smart, but they may not be smart enough to do this. The compositional nets are a little bit smarter because they've got generative, and classic models going back to the 1980s for dealing with occlusions used generative models, because with generative models there's a natural way to detect occluders. To compete with deep nets, of course, means developing compositional networks. You make them generative on the deep network features, not on the image intensities themselves, because you want to be invariant to the variability between different airplanes, etc., and that's what deep network features is designed to be. But you can make compositional models on the deep network features. these models can be trained end-to-end using backpropagation and clustering. The inference is pretty similar to standard deep networks, just fast, bottom up, and a little bit of top down. The training is, so the training and testing is fairly similar. This is work in progress. We have things working on 12 types of objects shown in CVPR. Later work we've got 50. But I still have to say that I like compositional networks. I think they've got very nice properties like generative things. For me, these are very much the starting point. There are certain limitations, which I'm well aware of, and those are things we're working on improving. So, from a perspective here, what's happening, deep networks are just given training data. They're not given any extra knowledge about the world. Humans at least know there are parts, there are objects, they can be occluded, etc. And so the challenge of occlusion are partially being overcome by introducing prior knowledge about the composition model, the partial occlusion and context into the neural architecture. So anyway, so that's the work I'm presenting, and I hope you find that interesting, and maybe if you're interested more about compositional models, contact us and let us know about it. So I've now gone a little bit over the slides, over time. We've got robustness to occlusion on 12 objects being extended to more in submission. There's some references here if you want to dig up more about them or contact us. Otherwise, thank the organizers again for inviting me to this talk. I think getting algorithms to work on images of low quality is very important, and for me, occluders are the ones that I'm particularly interested in at the moment and have been focusing on. So thank you for your attention.